Good morning, everybody. Today we will cover approximately 2.5 sections. To be honest with you, I tried to catch up. I tried to finish the material for our test 2 even before the spring break. And we are supposed to be at the end of 4.3 at this point, actually. But your material for test 2 will be only up to test 4.2. Topics material for test 2. You know what? Let me make sure. The material for test 2 will be up to 4.3 actually. So up to section 4.3. Okay, so to be more precise, that will be from 2.7 2.7 and then 3.1 to 3.6, 4.1 to 4.3. Now 3.6 is an easy material. Again, the assumption is you already watched up to lesson number 12. We are supposed to be at lesson number 13 today, but we are one day behind schedule. That's okay. That's okay. But yeah, we'll do just a little bit of 3.6 and then our focus will be more on 4.1 and 4.2. Now, what about variation that we need to learn? There are two big terminologies. The first one is what they call direct variation, or sometimes we call that proportional. Now, if two variables, let's say x and y are proportional, then what it means is the ratio x over y equals to constant. That's actually the word proportional means. The ratio is constant, okay? Or we can also say that x is a constant multiple of y. Okay. Proportional directly varies directly, means if one of them increase, then the other one increase. If one of them you doubled one of them, then the other one also get doubled. Now, the next terminology is inverse variation. Inverse variation, or inversely proportional. If x and y are inversely proportional, then what it means is x times y equals to a constant. The product is constant. If one of them increase, the other one decrease. If one of them being doubled, then the other one being half. Or sometimes we write it as x equals to k over y. Okay, so actually from this section, you just need to memorize these terminologies. What does directly proportional, direct variation, inverse variation, inverse proportional means? That's all you need to memorize. That's all you need to memorize. Now, for example, I will do, I think, 4 problems from here. Okay, I will do 4 problems from here so that you see the application of the work. Number 4, the easiest one, S is directly proportional. And they actually don't need to use the word directly if they already say proportional. Okay, now S is directly proportional to the square of X. You know what? Let me mark it in yellow. From that yellow color, then we get this right away. S equals to K times the square of X. Okay, that's what we know. Then from the second sentence, when X equals to 2, then S equals to 24, I plug in numbers. 24 equals to K times 2 squared. Now from here, we will get the constant of variation. Our textbook called that constant of variations, and actually plenty of textbook call that constant of variations for the K. But K is actually a more appropriate terminology, supposed to be coefficient of variation instead of constant of variation. Okay, so some textbook quite 50-50. Some textbook call that constant of variations, some other textbook call that coefficient of variations. But from what you see here, it's supposed to be coefficient. It's supposed to be coefficient. Okay, yeah, but I don't mind. You call that constant, you call that coefficient of variations. It's either way is okay. So from here we get K equals to 6. Therefore, the equation is the equation is now S equals to 6x squared. Now, this is the constant of variations, and this is the equation. That's for number 4. That's very easy. Okay, that's the equation, or that's the formula. Number 10, now it gets a bit more complicated. There are 2 sentences here. Z is directly proportional to the product of X and the cube root of Y. So C is equal to constant multiple of the product of X and the cube root of Y. Or we can simply just say Z equals to KX cube root of Y. Now that's from the first sentence. Now then, the second sentence, we plug in numbers. When X equals to 2, when X equals to 2, and the Y is 8, then the C equals to 12. Okay, then I solve it. That's 12 equals to K times 2 times 2. That 12 equals to 4K. So K equals to 3. Now that's the constant of variation. And therefore the formula is C equals to 3x cube root of Y. Easy enough? You know what? Let me add one more problem before I work with the further word problems. Give me a second. Something with joint variation. I will take a look on number 8. What happened? Number 8, y is directly proportional to x. Let me insert that here. Y is proportional to x and inversely proportional to the square of x. So y is directly proportional to x means y equals to kx. And inversely proportional to the square of z. That means over c squared. Take a look. Now we call this joint variations. We call this joint variations. It's proportional to x and inversely proportional. You have the proportional and inversely proportional case in the same formula. Okay, now so that's the expression. That's the basic formula. Now let's find the k. If x equals to 4, c equals to 3, then y equals to 16. So 16 equals to k times 4 over 3 squared. That's 16 equals to k times 4 over 9. I will multiply by the reciprocal. So 16 times 9 over 4 equals to k. So k equals to 36. Is it right? 4 times 9, yeah. K equals to 36. Now that's the constant of variation. And the formula, therefore, y equals to 36x over c squared. I hope after going through those polynomial and rational functions, then this feels like a Mickey Mouse for you, supposedly. Yeah, supposedly. Now, one of the reasons we learn this is because in calculus later on, especially chapter 4, you will see a lot of word problems. Chapter 4 in your calculus class later on, there will be a lot of word problems in which you talk about proportional, inversely proportional, and applying the derivative, basically calculus analysis there. Now then, for the next 2 questions, we learn how to construct the equation, okay, and then make some conclusion from those. Number 24, the range of projectile. It is known from physics that the range R of a projectile, R, is directly proportional to the square of velocity. Oh, that's our part A. Huh. That's our part A. Now, part B. A motorcycle daredevil has made a jump of 150 feet. So that 150 feet is the R. Okay. And then if the speed coming off the ramp is 70 miles per hour, find the value of k in part A. So I plug that in. That's 150 equals to k times 70 squared. Then we compute 50 equals to k times 4900. So k equals to 150 over 4900. Simplify, but do not make it decimal. Because if you make it decimal, there could be some rounding error there. Just simplify, but don't make it decimal. Okay, unless if you make it decimal, you get a very nice number. Otherwise, leave it like this. Okay, I think I can reduce by 5 here. Yeah, I can reduce by 5. If I reduce by 5, it will be 3 over 98. Okay, now that's for part B. Now part C. Let me continue next to it. The formula at this point is r in feet equals to 3/98 v squared in miles per hour. Now, suppose the daredevil can reach a speed of 80 miles per hour. Estimate the possible length of jump. So what is the range if the speed is 80 miles per hour? So r equals to 3/98 times 80 squared. Now then you use your calculator. 3 times 6400 over 98. Okay. 3 times 6400 divided by 98. That will be 195 something feet. Okay. So using the result from that 70 miles per hour, that gives us 150. Then if you want to jump like 200 feet, then your speed will be, of course, more than 80 miles per hour. Okay, should be more than 80 miles per hour. If you want to get 200 feet, more than at least 200 feet. That's for number what? That's for number 24. Let me go on. Now, this is the type of question you see in Calc 1, actually. This is the basic part. Okay. A flat metal plate is positioned on an XY plane such that the temperature T is inversely proportional to the distance from origin. That's inversely proportional to the distance from origin. Okay, now then, they know that the temperature at point 3,4 is 20. So 20 equals to K over the distance of that 3,4 from the origin. So what is the distance of 3,4 from origin? Three comma 4 from origin. 1, 2, 3, 1, 2, 3, 4. What is the distance? Now you see that you use coordinate Cartesian Pythagorean theorem, right? Okay, so this is equals to the square root of 3 minus 0 squared plus 4 minus 0 squared. Get the boom, that's equals to 5. So the distance is 5. When the distance from origin is 5, the temperature is 20. Now, therefore, what is K? K is 20 times 5 equals to 100. Now, we update the formula now. Therefore, the formula becomes T equals to 100 over D. Now, then we go to second stage. Find the temperature at the point 24,7. 24,7. 24,7. This is 3,4 here. How about at 24,7? Then let's find what is the distance. The coordinate 24,7 the distance from origin will be 24 minus 0 squared plus 7 minus 0 squared. Gada boom, that's 25. By the way, that's one of the special Pythagorean triplets. If you remember your geometry, Pythagorean triplets, the important Pythagorean triplets are 3, 4, 5. Right? 3 squared plus 4 squared equals 5 squared. 5, 12, 13. 7, 24, 25. 8, 32. Hold on. 64. 8, 15, 17. In fact, these are the most commonly used Pythagorean triplet. Now we will get to this Pythagorean triplet even more once we start chapter 5 or chapter 6 when we do trigonometry. So what will the temperature be? The temperature at 24,7 is 100 over 25. Okay, so the temperature is equals to 4. Okay. And that's basically it for this section. Yeah, that's basically it for this section. As I remember, I don't really ask questions from this 3.6 in my tests too. I have never. But I plan this time I will ask questions from here, but it will be a simple one. Something like the last 2 questions, like word problems. But this section itself is very simple. So I don't think you should worry about this section. Okay, now let's go on to 4.1. 4.1 is on inverse function. Again, my assumption is you already watched the lecture video, and I will just continue from there. I would like to go over some basic first, okay? But important basic. First, about definition of one-to-one. A function is one-to-one is a one-to-one function if, so you say that a function is one-to-one function if there are 2 ways to define it. First, x1 not equal to x2. As long as the x are different, then fx1 is not equals to fx2. Okay, a function fx is one-to-one if different x gives us different y's. And we have actually plenty number functions like this. Every linear function whose slope is not 0, if every linear function whose slope is not 0 is one-to-one function. Yeah, let's say, for example, y equals to 2x minus 1, right? You plug in different x, the y will be different. Okay, now equivalently, now that statement number 1 is equivalent to if the y value are the same, then the x value must be the same. Now, one way to prove that a function is one-to-one is using this second definition. Okay, we use definition 2 to show that a function is one-to-one. Okay, at least at this level. Once you go to calculus 1, then they introduce you with another method. Okay, actually you will see one of the consequence from the graph is this. If a function is continuous on an interval from A to B, and I think I should say continuous n monotonic on interval A to B, then the function is one-to-one on that interval. Now the word monotonic means increasing or decreasing. Decreasing all the way, decreasing in that interval, or increasing in that interval. Okay, you can see, like, for example, a linear function is strictly increasing or strictly decreasing, right? Then it makes the function one-to-one. Okay, now x cubed, the graph of x cubed is also strictly increasing. The graph of x cubed is also increasing. So it is also one-to-one. It is also one-to-one. Okay, now another one. So important notes. Another important notes. The graph of a one-to-one function must satisfy horizontal line test. That is, every horizontal line intersect the graphs at most at one point. So if you are given the graph, okay, see if you can get a horizontal line that touch the graph twice or more. Okay. Now, let's do some basic problems from our textbook. I will grab problems from section 4.1. Give me a second. I want to do easy one first. For example, we take a look on number 4. Hold on, where's that? I honestly get distracted with my children next to me. Give me a second. number 4. We see number 4 here. We have ABC. Which of this graph is a function? Let's start with function. Okay, let's start with a function. Okay, is 4a a function? Now it needs to pass vertical line test, right? So 4a is a function, right? Part B, graph B, it also satisfies vertical line test. So it is a function. Okay, but part C is not a function, right? It's not a function. Now to check one-to-oneness, you do horizontal line. Now here for A, you can pull a line that gives you intersect at three different points, more than 1 point. So once you can find such line, it means that function is not one-to-one. Okay, now part B, when you pull horizontal line, sometimes it doesn't touch it at all. So sometimes it touch it, but even if it cross the graph, it will touch it at most at 1 point. So this function is one-to-one. Now part C is not even a function, so it won't be a one-to-one function. Okay, so we can say that an equation is a one-to-one function if the graph satisfies both horizontal and vertical line tests. Like part B, it has satisfied vertical and horizontal line tests. Part A only satisfies vertical line tests, not horizontal line tests. So it is a function, but not one-to-one. Now, part C, once it is not a function, we don't talk about one-to-oneness. Okay? So we don't have a situation where the graph is a one-to-one but not a function. No, there's no such thing, at least not at this level. Okay, now notice that in part B, we see that it is one-to-one, right? At the same time, notice that the graph is increasing. Notice that the graph is increasing. Like if you are here and then you try to go to the other side, then you need to walk up. You need to walk up. If the graph is strictly increasing or strictly decreasing, then it is one-to-one. Okay. For C, we don't have to check one-to-one because it's not a function. You are correct. Once it is not a function, then we can't even talk about one-to-oneness. Okay, because one-to-oneness is something we consider after we have a function. Okay, one-to-oneness is something we consider after we have a function. Okay, that's about one-to-one. Now, I have some question from our textbook in which I didn't go over in my previous lecture about how to check if a function is one-to-one or not one-to-one. I want to see number, what happened? This one's here. between number 6 to number 16. I never really go over this in my previous lesson. Now is the time I go over that. Okay. How do we know that a function f is one-to-one? One way, of course, you look at the graph, right? Okay, but how to effectively show that a function is one-to-one or not without graphing? Okay, for example, number 6. Maybe number 8 first. Number 8. Is fx equals to x squared plus 3 one-to-one? The way we think about that is like you need to first decide, is it one-to-one or not? Give me a second. From the sketch of the graph, we know that it is not one-to-one, right? Because I can go with one horizontal line that intersect two different axes, right? So use that argument. Choose a y. So solution, you will say no. Why? Because you just need one counterexample. Because for y equals to, let's say, 4, okay, for y equals to 4, okay, then we will get x squared plus 3 equals to 4, x squared equals to 1, x equals to plus minus 1. Okay, in other words, for a y, you have two different axes. So what end up happening is this: you now have x equals to 1 and x equals to -1. They are not the same, but f1 is equals to f -1, which is 4. So it is not one-to-one. Now, to show that it is not one-to-one, you just need to show a counterexample. Give a y that pick a y that gives you two different axes. Okay. Now, how to show that it is one-to-one? How to show that it is one-to-one? Let's say easy one first. Number 6. fx equals to 1 over x minus 2, one-to-one. How do we show that a function is one-to-one? Well, first you look at the graph. This is the graph of 1 over x that you move 2 units to the right. So it looks like this. Okay, and every horizontal line you pull, it intersects the graph at most at one point. Right? So the function is one-to-one, but that kind of argument is actually not enough. Okay, that kind of argument is not enough. Well, because I can argue with you, well, because you draw your graph not big enough such that you don't see a horizontal line that intersect two different points, right? Okay, but it gives you a feeling that, hey, you know what? I think it is one-to-one. So, you know what? I should not erase that. I feel it is one-to-one, but let's take a deeper look. What I will do is, I select solution. So we will say yes. Now then, because suppose fx1 is equals to fx2. Remember this definition I said earlier? Suppose you start with this. Show that it leads to this. Suppose the y's are the same, then the only consequence possible is that the x's are also the same. Okay, suppose fx1 is equals to fx2. Now then, it means 1 over x1 minus 2 is equal to 1 over x2 minus 2. Now, suppose they are equal, we need to show that the consequence is the x also equal. Now, I do the reciprocal for both sides and add 2 to both sides. You see that the assumption of the value of this function is the same, leads to the conclusion that the x has to be the same. Okay, so we conclude. So fx is 1 to 1. Now, number 6 is a very easy example. Number 6 is a very easy example. Now, number 14 may not be that easy. Is fx equals to 2x cubed minus 4 1 to 1? Let's have a feeling first. X cubed looks like this. That's what the graph of x cubed look like. Okay, 2x cubed basically stretch that vertically by factor of 2, and subtract by 4 means you lower the function 4 units down. So the graph becomes approximately something looks like this. But it is still 1 to 1 though. You see, if I pull any horizontal line, it will intersect the graph at most 1 point. So we feel that it is 1 to 1, right? Again, feeling is not a good guide. Just like graph may be deceiving. Right? Now, then we suppose now we prove this analytically. Suppose we have fx1 equals to fx2, which means 2x cubed minus 4 equals to 2x2 cubed minus 4. You add 4 divided by 2, then you get x1 cubed equals to x2 cubed. Now, when I apply cube root, then I get x1 equals to x2. Right? Now, cube root is a one-to-one operation. Cube root is a one-to-one operation. So when you apply cube root, that will be, you don't need to use plus minus, right? Okay, now because it leads to the fact that x1 equals to x2, then fx is 1 to 1. Now, notice that this way of proving cannot be used against number 8. You cannot do that against number 8. Let's say, suppose you try to force that, that let fx1 equals to fx2 for number 8. Okay. So x1 squared plus 3 equals to x2 squared plus 3, right? Subtract by 3, you get x1 squared equals to x2 squared. Is it right? So it actually boils down to, can you find two different numbers whose squares are actually the same? Now, if you apply square root property here, you'll get x1 equals to plus minus x2. Okay, so it is possible that you have the same y's, but the x's are actually opposite. Okay, which implies it means it does not imply x1 equals to x2. Right? So that's another way to prove that, even though in practice, if you want to show that a function is not one-to-one, just show a counterexample. Show a counterexample. Find a y that gives you, that comes from two different axes. Okay, to show that it is one-to-one analytically is harder. Okay, once you are in calculus 1, then they have different way to prove that. Okay, but for now, to prove that a function is one-to-one, basically this is the only way. Okay, basically this is the only way. Now, if I go back to number 14, the step from here to here, what I did there, usually not acceptable once you are in much higher level. If you are in 300, 400 level, then I cannot just say that x cubed equals to y cubed implies x equals to y. That is not true. Okay, the proper work supposed to be, the proper argument supposed to be. So I'm trying to show you what will happen later on once you go even further than calculus. If you are in electrical engineering, if you are in industrial engineering, so not only if you are in math, if you are in physics, okay, then you need to show more details, and that work is not acceptable. Not acceptable at much high level. Okay, it's way beyond the scope of our class, but let me show you the way it's supposed to be done. You're supposed to set it equals to 0 and then solve it from there by factoring. So this is x1 minus x2 times x1 squared plus x1 x2 plus x2 squared equals to 0. Okay, where either x1 minus x2 equals to 0 or x1 squared plus x1 x2 plus x2 squared equals to 0. Now we get the one we want here, x1 equals to x2. But is it possible that we have an x1 which is not equal to x2? And when you put them together here, we get equals to 0. Now, the way I solve that will be, I will use quadratic formula. It could be a bit confusing. Okay, let me change x1 becomes a and x2 becomes b. Okay, then I hope you see the quadratic function there, where a equals to plus, negative b plus minus square root of b squared minus 4ac over 2a. So a equals to negative b plus minus square root of negative 3b squared over 2. So do we have x2 different from x1? But when you plug that x2 and x1, the result is 0. The answer is yes, there is such number, yet that number has to be a complex number, because this will give us negative b plus minus b square root of 3i over 2. Okay, in other words, this function is one-to-one on real plane Cartesian coordinate system, but it is not one-to-one in complex system later on. That's what I say that this is much, much higher level. Okay, so is there two numbers, two different numbers that when you do this operation, the result is 0? And the answer is yes, you have such thing, but one of them, at least one of them, has to be a complex number. But we are dealing with only real numbers here. Okay, so no such real A and B. Okay, that's actually the proper argument. So that requirement that fx1 equals to fx2 implies x1 equals to x2. This is the correct argument. Okay, at your level, yes, you don't deal with complex numbers, right? So you can go ahead here. Okay, now notice that if I go back to these steps here, if you want to do it correctly, then it's supposed to be x1 squared minus x2 squared equals to 0. You factor it, and then you'll get x1 equals to x2, or that's the one kills the one-to-one, x1 equals to negative x2. Okay, now again, as I remember, I have never asked such question in my tests. And to be honest with you, I don't have that interest to ask such question. I just try to instill in you that if you are going to those hardcore math major, like math major, physics, electrical engineering, where you need to do a lot of proving, theoretical analysis, and therefore proving, then the way you show your argument should be very critical. You cannot just say, oh, from here to there. And then somebody come up with, you know what? Like for example here, right? When you say, oh, if x cubed equals to y cubed, then x equals to y. And somebody's come up with, no, that's not always true. I can find two different numbers, but the cubes are the same. Okay. So that's the strictness of proving. Now, let's go on. Suppose we already have a one-to-one function. If a function is one-to-one, and this is big, important. If a function fx is one-to-one, then D inverse is also a function. And can use the notation F inverse X. Okay, now I believe I mentioned this in my lesson before, and I want to mention that again here. Something that not a lot of instructors agree with me, but hey, you know what? I know what I'm talking about. Okay. This statement, every function has an inverse. Our textbook, just like a lot of pre-calculus textbooks, if not all, always talk about inverse function under the context of one-to-one function. So as if we say this, as if we are saying that the function has to be one-to-one Then you talk about inverse function, and then you talk about inverse. Then you can talk about inverse, but it's actually not true. It is actually not true. Okay, that's not true. Okay, that's not true. A function doesn't have to be one-to-one for us to talk about the inverse. No, it doesn't have to be. It is that the inverse is a function if it is one-to-one. Every function has an inverse, but not every inverse is one-to-one. It's a function. No. A function has an inverse, but the inverse of every function doesn't have to be a function. Now, let me show you an example. Okay, if you have not watched my video, lecture video, then it could be confusing for you. So let me show you this function. Let fx equals to, let's say, x squared minus 1. Now, this function is definitely not one-to-one because it doesn't satisfy horizontal line tests. Okay, but can we find the inverse? Yes. Okay, this function is the same to, is equivalent to y equals to x squared minus 1. Okay, the inverse of that function is x equals to y squared minus 1. You switch the x and the y. X becomes y becomes x. That's it. You got the inverse. What is an inverse, Thomas, to start with? An inverse is the inverse of a function undoes what that function is doing. Okay, so for example, in this function here, f1 is equals to 0. Okay, so in our mapping, 1 goes to 0. Right? That's what this function is doing. Now, inverse does this. Inverse sends that back. Inverse undoes that. Inverse undoes that. Okay, so 1 goes to 0, 0 goes to 1. Okay, even though in this case, 0 also goes to -1. So to find the inverse of a function, you just swap x and y. X becomes y becomes x. You got the inverse of a function. However, this inverse is not a function. This inverse is not a function. Why? For some x, you get 2 different y's. So then we cannot apply this notation, the functional notation. It is ridiculous, right? This notation here means the inverse is also a function, but that's not true. Why? Because you can find some x, let's say x equals to 0, that gives you 2 different y's. Okay, so let me emphasize again. Every function f has an inverse. Okay, but the inverse of a function may not be a function itself. And therefore, has no right to use that notation F inverse X. Only if the inverse is also a function that you can use, you call that inverse function. So the word inverse function is not the same to the phrase inverse function is not the same to the phrase inverse of function. No, it's not. Okay, that's it took me a while to realize that students misunderstand these two phrases here. They are not the same. Inverse of a function always there. We always have the inverse of a function. But that inverse may not be a function. Okay, so when we use the phrase inverse function, then it refers to an inverse. That inverse is a function. Okay, now while the phrase on the left-hand side, it simply talks about the inverse of a function. It doesn't say that inverse is a function. Okay. Now, next, how to find inverse of a function. If a function fx is one-to-one, then the inverse is also a function. And in fact, and also a one-to-one function. So even the inverse will be one-to-one. Oh, Thomas, I start getting I start getting lost. Okay, let me say it again. If you have fx, okay, it has inverse. But not that inverse is not inverse function. Okay, now if fx is one-to-one, a function one-to-one, then it has inverse. And you can use the inverse function notation. So the inverse is a function in itself. And the bonus is, and that inverse function is one-to-one. Now, what I want to do now is to show you how to find the inverse function of a one-to-one function. How to find inverse function of a one-to-one function. Now, I made that in my lesson that you have to use this four-step procedure. Step one, replace fx by y. So let's say, for example, an easy one, let fx equals to 2x minus 1. Okay, so your step one will be replace fx becomes y. Your step two, you swap x and y. So step 2, y becomes x becomes y. Step 3, solve for y. So x plus 1 equals to 2y, y equals to x plus 1 over 2. And step 4, the last one, replace y by f inverse x. Okay, now procedures 1, 2, 3, 4 should be explicitly named, written in your work. In my class, I require you to do it this way. Okay, and you will see later on why is it so important to show it this way. Okay, because I will modify these 4 steps in future for other purpose. And I don't learn it from me though. It's not like Thomas come up with his own way to do things. No, I learn it from my professors too. Okay, it's not, I'm not that good. I'm not that good in inventing new things. And even if I come up with a new thing, I usually ask my colleagues, especially my professors. I go back to my university and ask them. Or I ask other people whose expertise is verified. Okay, but I don't come up with this myself. Okay, I learn it this way, such that I really see the details and I can teach you that detail right now. Okay, do it in these 4 steps. You even need to write these 4 steps. 1, 2, 3, 4. Remember the 3-step procedure when we solve nonlinear inequality? Step 1, critical number. Step 2, sign graph. Step 3, solution. Right? Now, when you are finding inverse function, you are also required to write this step 1, 2, 3, 4. Okay, now for the next approximately 15-20 minutes, I will do examples where we find inverse function of a one-to-one function. Okay, now you will see that the difficulty level actually gets it gets more difficult as we progress. Let's start with number 29. I don't remember what problems I did in my lecture, so I do odd numbers so that we don't have overlap. Number 29, find the inverse function. Find f inverse x of fx equals to 3 over 2x minus 5. Now, from our graphing rational function, we know that this function is one-to-one. I wonder if you remember that. Okay, but you should be able to sketch this graph already though. Okay, but let's try to sketch this graph. So you see we don't have x-intercept, we have y-intercept 0, negative 3/5. Okay, we have vertical asymptote, x equals to 2.5, 5/2. Horizontal asymptote is y equals to 0. Okay, then you will see later on that the graph looks like this. So it is a one-to-one function. Right? It is a one-to-one function. Now, they don't ask you to prove that anymore. They don't ask you to prove that anymore. Once they ask you to find the inverse function, it means it is already assumed that it is one-to-one. Okay, it is already assumed it is one-to-one. Now, find the inverse function. So how will you show that? I need you to show it like this. Step 1, write it down. 1. Y equals to 3 over 2x minus 5. Step 2, you swap the x and the y. Step 3, you solve for y. So multiply both sides by the LCD. That's a common practice though. And then distribute 2xy equals to 3 plus 5x. So y is equals to 3 plus 5x over 2x. Therefore, step 4, f inverse x, the inverse function, is 3 plus 5x over 2x. Now, remember I said earlier that once you swap the x and y, you actually get the inverse already. Okay, so the inversing is actually done at this step. Inversing is done at this step. Okay, now this is to write the inverse as a function. Okay, now one big phenomena of a function and inverse function are the role of x and y being swapped. For example, if we use this example number 29, we are done with the question. The question is just to find inverse function, right? But I want to do further analysis here. Okay, for example, can you tell what is the domain of the function? The domain of the function is all real numbers except 5/2. I mean, we know that from rational function we learned 2 days ago. Okay, now notice that this domain of the function is equal to the range of the inverse function. That's equal to the range of the inverse function. If you sketch this graph here, the vertical asymptote is x equals to 0. Horizontal asymptote is y equals to 5/2. Okay, and then the x-intercept is -3/5. So from here you see that the range is all real number except -3/5. I'm sorry, except, no, that's 5/2. Y equals to 5/2. All real numbers except y equals to 5/2. Right, that's the range. So maybe I write it this way. If this is the function and this is the inverse function, the domain of the function is the same to the range of the inverse function. They are related. Okay, and if you take a look on the domain of the function, in this case, the domain is of the function of the inverse function is all real number except 0. Right? Now, the domain of that inverse is actually equals to the range of the function. Now, what I want to say, this last summary here is important, because if I ever ask you what is the range of a function, one way to do it is to find the domain of the inverse. Okay. Now, another thing is that for fx, what is the y-intercept here? The y-intercept of this function is -3/5, right? Now, that is related to, not equal, of course, as a coordinate, they are not equal, okay, but related to the x-intercept of the inverse. You see the y-intercept here is 0, negative 3/5. Right? That's the y-intercept. Now, the x-intercept of the inverse is negative 3/5, 0. Remember that we swapped the x and the y? Right? That's what happened. That's what happened. The x-intercept becomes y-intercept, y-intercept becomes x-intercept. In fact, the horizontal asymptote later on becomes vertical asymptote. Take a look. The horizontal asymptote of this function is y equals to 0. Right? The degree on the top is less than the degree at the bottom. So the horizontal asymptote is y equals to 0. Right? Now that horizontal asymptote, when you do the inverse, it becomes the vertical asymptote, x equals to 0. And vertical asymptotes in the original function becomes the horizontal asymptotes. It's like once you switch the x and y, then x, the domain becomes range becomes domain, x-intercept becomes y-intercept, y-intercept becomes x-intercept, horizontal asymptote becomes vertical asymptote becomes horizontal asymptote. Okay, now let's do a more problem like this. Number 31. Okay, let fx equals to 3x plus 2 over 2x minus 5. And the question is find the inverse function of x. Now, in fact, I would like you to do this together with your break later on, but I want you to go even further. Okay, use that inverse function to find the range of this function. Now, for you to find that, it's basically asking you what is the domain of the inverse function. Okay, consider that like a follow-up question. Now, let me ask you to do this first. Inverse of this function is very similar to what we have up there. It's very, very similar to what we have up there. Okay, do it in 4 steps. Replace the fx by y, second, swap x and y, third, solve for y, and then fourth, write that as f inverse x. Okay, that should take you like around 5 minutes. Together with our break, 10 minutes. We come back at 9:35. Okay, while waiting for you, working on that or coming back from your break, let me start working on this problem. So my step 1, y equals to 3x plus 2 over 2x minus 5. Step 2, I swap the x and the y. Step 3, I solve for y. So 2xy minus 5x equals to 3y plus 2. So those terms with y, I put together on the left-hand side. And the one without y, I put together on the right-hand side. Now then, I will factor the y. So the y is 5x plus 2 over 2x minus 3. Now finally, step 4, then the inverse function of x is therefore 5x plus 2 over 2x minus 3. Okay, so we are done with that question. We are done with this question. Okay, we are done with that question. Now, the follow-up question is then, what is the range of that function? The range of the original function. You can actually look at the graph of this function and see that the range is all real numbers except 3/2. Okay, but a better way to look at that is to look at the inverse function. This is the inverse function. What is the domain of that inverse function? The domain of that inverse function is all real numbers except 3/2. Right? Now, suppose another follow-up question. So that's all part A. How about find the y-intercept of the graph of inverse function? The y-intercept of the inverse function is equivalent to the x-intercept of the function. Okay, now the x-intercept of the function is -2 over 3, 0. So what is the y-intercept of the inverse function? Without graphing it, in fact, without even finding the inverse function, you can just look at that. Oh, then the y-intercept of the inverse function must be 0, -2 over 3. Okay, notice that I swapped the x and the y. I swapped the x and the y. Okay. Now, both of these, number 29 and number 31, even though I do these examples here, are considered easy part of inverse function, and I always ask this type of question in my intermediate algebra class. So I do not look at number 29 and 31 as a problem, a question that belongs to pre-calculus class. No, it's lower. It's something you should have done before. We just review it right now. So what kind of inverse function problem, Thomas, that belongs to pre-calculus class? The one that requires more analysis. Let's say, for example, number 33. Okay, let fx equals to 2 minus 3x squared. X is less than equals to 0. Notice that if they don't tell us x is less than equals to 0, then the function is not one-to-one. Oops. If they don't tell us that x is less than equals to 0, then the function is not one-to-one. Give me a second. So our friend asked a question, Thomas, can you go over that y-intercept of the inverse function? Now, remember that x-intercept and y-intercept are related. Okay, y-intercept of the function, it will tell us the x-intercept of the inverse function. The x-intercept of the original function will tell us something about the y-intercept of the inverse function. Okay, something I wrote here. This guy. Okay, if you want to find out the x-intercept of the inverse function, then you look at the y-intercept of the function. If you want to find the y-intercept of the inverse function, what you can do, you look at the x-intercept of the original function. Now, so the question we have at hand earlier is find the y-intercept of inverse function. Now, to find the y-intercept of inverse function, I will look at the x-intercept of the original function. Now, this is the original function. Now, what is the x-intercept? You set that equals to 0, right? So you get 3x plus 2 equals to 0, x equals to negative 2/3, right? That's the x-intercept of the original function. Then what is the y-intercept of the inverse? Then you swap the x and the y. Okay. If you go to field, a major called industrial engineering, or in other place they call that operational research. I think in America they call that industrial engineering, but in other countries they call that operational research. That's basically using math into production. Like if you have manufacturing, right? Okay, so they use what they call operational research. Now, in that field, there is something called dualism. Dualism is like either you look at the function or you look at the inverse function, kind of like that idea. Okay, so I ask you, as if we are living in two worlds, two parallel worlds, the world of the function and the world of inverse function. Okay, now, so there are some questions here that is hard to answer. For example, the range. Okay, usually it's hard to answer that question now, but it will be easier for us to look at the mirror, the dual first, and find what is the domain there. Now, the domain of your inverse function will give you the range. Okay, so creating a dual, like in this case, the inverse function, enable us to see that from the third party. Let me give you a little illustration. This illustration may be funny, but it is true. Okay. a little information about me. Okay. I don't really shave. Well, I do shave. Okay, but I don't really shave. Okay. I pull my hair, like on the mustache, okay, under my chin. I pull them. Okay, I use a pinset and then I pull them. But I cannot really do that if I don't have a mirror. You see it? Okay, let's say imagine this is Thomas, right? And he has some mustache. He needs to pull it out, but he cannot look at the position, so he uses a mirror. Then he can pull it out better. Right? Now think of that as the inverse function as your mirror right now. Okay, something that you cannot do directly on your own, but with a mirror, you basically look at your inverse function, you look at your shadow, okay, and you imagine whatever you do on that shadow, that's what you do to yourself. Okay, but of course your left becomes right, your right becomes their left. Okay, that's just my little illustration. Now, the thing is that method is being used a lot. This dual idea is actually being used a lot in operational research. Okay, operational research is actually a field in math, very, very big in Asia, however, but in America, it's not as big. In America, it's not as big. They call that industrial engineering here. But I guess you don't really hear that terminology, that people don't really know that we have some such major. Okay, industrial engineering. Now, industrial engineering, some little history or background. Industrial engineering, originally very well developed in Europe and being used a lot in oil exploration in Middle East. But then in the last 10, even 20 years, okay, industrial engineering is very, very well developed, very, very well developed in China and Korea. Okay, so you can say the orientation of industrial engineering, or we call that operational research. Is very, very well developed in China and in Korea, okay, especially China. Now, why I say China? Because China can build a building that America takes 2 years. They can build that in 2 months. Why? Because they do research, okay, and then they can operate in a very, very efficient way with all the laws still being in place. Like you can give some, you can put some laws here and there, and then America will work with a lot of paperwork. You need to do this first, and then you need to get this. You need to get this. Let's say if you want to build a factory in America, in US, right? You want to build a factory. Okay, then first you need to get a lot of permit, right? The permit for the land, the permit for the operations, what kind of factory you need, and so on and so forth. But if you let somebody with operational research background to work on that project. Oh, by the way, another terminology they use here is called project management. So basically, the project manager will work on the permit on the land, permit for the factory, permit for this. At the same time, they get the land. At the same time, they already order from somebody else all the building block for their factory. They already ordered the machines, so on and so forth. So once the permit, all the permits come, they already start building. And when they build, they don't really build like, for example, they put the stone one by one with all the cement one by one. No. Once they have the foundation, they already come in walls. The wall already there. They just need to stack them. It becomes like a Lego. Okay, they don't put the cement there and wait until it dries. No, they already make the wall somewhere else. They just bring the truck with the wall already made. Okay, instead of bring a truck with the blocks and the cement, they bring the wall. Okay, the strange thing is, believe it or not, bring the wall. After all, you use a big truck, right? Okay, so bring the wall like that, actually less hassle. Okay, you don't need to mix the in the project place. No, you already have the wall. Okay, so that's why they can finish that building in a lot earlier time. Okay, now in this case, I believe America should learn from them. Okay, yeah, we should learn from them. Or maybe we already have that though, but it's not really easy to apply in America yet because not a lot of people have that skill. Okay, so that's one thing you want to learn. If you want to bring manufacturing our factories back to America from those countries, right? You can say that, oh, America, you know, we don't really produce anything. Oh, everything's produced in other country, either in India or China. Well, they can produce it there more efficiently and cheaper because what? Beside maybe because it's cheaper employment there. Like I mean Indonesia too. Okay, actually Indonesia is a lot cheaper, right? But it is possible that their skill in finishing a project, in this case, operational research, industrial engineering, program, project management, is a lot more advanced than what we have here. Okay, so one thing you can do if you want to improve our manufacturing in America, then focus on those kind of things. Okay, now let's come back here. Let's come back here. Now, this function originally not one-to-one until we restrict the domain to only from -infinity to 0. Okay, now then, one way to make a function which is not one-to-one becomes one-to-one is by restricting the domain. Okay, now then, how do we find the inverse function? Now, let me show you how somebody from intermediate algebra will do this problem. So step 1, y equals to 2 minus 3x squared. Step 2, you swap the x and the y. Step 3, you solve for y. So 3y squared equals to 2 minus x divided by 3. And then y equals to, well, when you apply square root, you need to put plus minus. Now, at this point, I hope you realize that this is not a function. This is not a function. You have no right to write that as an inverse function. It is not one-to-one, right? I mean, it's not a function. So, but Thomas, they say that we need to find the inverse function. So what's wrong? Well, what's wrong is you didn't pay attention to detail. Okay, we need this thing. Then in step 2, when you swap the x and y, then the x less than equals to 0 becomes y is less than equals to 0. And that's what you carry through all the way. We didn't need it at that time, but I just keep on writing it down until when I have to make a choice, the y may be positive, may be negative, right? But because y has to be less than, the y has to be non-positive, then I will need to choose the negative branch. Okay, now it is a function. Therefore, we have the right to use inverse function notation. Okay, in other words, the restriction that they give you earlier becomes something you need later on. So write that restriction down, follow that. Now, that one is still an easy one. The harder one is actually number 37. Let fx equals to square root of 3 minus x. Now, we know this is a one-to-one function, right? Originally, square root of x, right? That's square root of x, and then I replace x by x plus 3, so it becomes 3 units to the left. Right, it is still one-to-one. And then replacing x by negative x, that's reflection with respect to the y-axis. So it is still one-to-one. Okay, so this function is one-to-one. So the inverse function must exist, right? The inverse must be a function and supposed to be one-to-one. Now let's work it out. Okay, the devil is in the detail. Step 1, y equals to square root of 3 minus x. Step 2, you swap x becomes y, y becomes x. Step 3, you solve for y. Now, the problem is, you may say this is your inverse function, but something not right here. The inverse, if it is a function, it has to be one-to-one, and this is not one-to-one. That is not one-to-one. So something wrong here, or something not complete, to be more precise. Okay, where's that? It has something to do with the domain and the range of your original function that you need to pay attention. Okay, remember when you square both sides, you have extraneous solution, right? At this point here, when you square both sides from here to here, you may have extraneous solution, right? So let's take a look on the range of that original function. Notice that for these, the range will be at least 0, right? I mean, that's automatic. I don't even need to write it down. Okay, so the y is at least 0. Now here, then x has to be at least 0 because you swap x and y. Now, once you square both sides, however, you need to avoid the x from running away from at least 0. Now, something that was not necessarily written, that's why I wrote that in blue. Now, in step 3, I have to write it explicitly. X has to be at least 0. Because in this equation here, x may be negative. X may be negative. You see what I mean? Okay, now that restriction becomes what you need to keep on writing until the end. So this function, f inverse x 3 minus x squared, is not one-to-one until you restrict the domain of that inverse function. But to restrict the domain of inverse function, you need to know the restriction of the range of the original function. Okay? Now, last question from this section. Last question from this section, number 47. The others are actually on the easy side. Yeah, but number 47, let fx equals to x squared minus 6x, where x is at least 3. Now find the inverse function. Okay, step 1, solution. Step 1, y equals to x squared minus 6x. Step 2, x equals to y squared minus 6y. Okay, so originally the restriction is x at least 3. Now the restriction becomes y at least 6, y at least 3. Now then, I solve for y, right? I think I can do completing the square here. So plus 9 equals to y squared minus 6y plus 9, where y is at least 3. So x plus 9 equals to y minus 3 squared. Okay, so y is at least 3. Now then apply plus minus square root of x plus 9 equals to y minus 3. So y is 3 plus minus square root of x plus 9. Right? Now the thing is, y has to be greater or equals to 3. That eliminates the other branch, the negative branch. As if I'm saying that this guy together with this guy give us only this. The y can be 2 values, but we also know that the y has to be at least 3. So the only way that y has to be 3 plus this blah. Then we can call that a function. With that plus minus earlier, we cannot write it as inverse function. No, it's not a function. This guy here is not a function. It's not a function. Okay, it is not a function. Until you incorporate the restriction into that equation, then you will get a function. Therefore, we have the right to write it as an inverse function. Okay. So f inverse x is now equals to 3 plus square root of x plus 9. Now, you won't be able to eliminate the negative part if you didn't follow this. So you have to write this all the way. Okay, you have to write that all the way. Now, that's about it for this section. I spend more time on working on this inverse function, especially the one with the restriction. Actually, I asked a very similar question in my Calculus 2. So next year, when you take Calculus 2, you may see this question. But when I ask this question, it's more about asking for their pre-calculus skill. Let me show you what I asked in my Calculus 2 test 1, number 2. Give me a second. This is what I asked. Let fx equals to x minus 5x squared for x greater equals to 1. Now find the inverse function. And all they need to do is actually do what I asked you to do. Okay, I even tell them be aware with the domain and range. So let's do this test 1, number 2 from my Calculus 2 class, which is actually a pre-calculus question. A bit more difficult for your level though. The number is not as nice. Okay, but step 1, y equals to x minus 5x squared for x is at least 1. Okay, step 2, x becomes y, y becomes x. And step 3, we need to solve for y. Is it right? Okay, so 0 equals to negative 5y squared plus y minus x. So if I use quadratic formula, then the a is negative 5, the b is 1, the c is negative x. The discriminant is b squared minus 4ac. That's 1 minus 20x. So y12 will be negative b plus minus square root of the discriminant over 2a. That simplifies to be 1 over 10 minus plus square root of 1 minus 20x over positive 10. But the y has to be at least 1. But you don't do restriction on the y though. You don't do restriction on the y. When you restrict the x, right? Okay, so even if I want to write f inverse x later on here, okay, then should I use the positive branch or the negative branch? Should I use the positive branch or the negative branch? Okay, I tell you, I will use the positive branch. Okay, but writing it this way is not enough. Why? Because your x may be 0. When x equals to 0, then f inverse x equals to 2 over 10, which is 1/5, right? The problem is 1/5 is not in the domain of the original function. Remember that the domain gives us the range gives us domain. Okay, so there's one restriction missing. One is restrictions missing. Saying that y has to be at least 1 is not enough. That's not the restriction. The restriction has to be done on the x, right? If you want to put restriction, then you need to put restriction on the x. But for us to have restriction x greater or less than equal something here, then we need to find the restriction on the y up there. Where's that? So what is the restriction of y here? That's what we need. Okay, now this is what we can do. Then I plug in when x equals to 1, f1 equals to 1 minus 5, that's negative 4. And using some calculus level question, we find out that the function is actually decreasing there. And actually we can see that here. For x greater than 1, give me a second. For x greater than 1, the function is actually decreasing. Okay, the graph actually not like that though. I'm sorry. The graph looks like that, but the cutoff point is not there. The graph here. This is x equals to 1. So the function is decreasing from there on, so that the range will be y is at most negative 4. Now that's what you will follow later on. So the y at least 1 enable us to choose which branch, right? Together with this, we get that positive. Okay, but the thing is, if you don't restrict the y, the x can be any number. Okay, the x can be any number, like even 0 when x equals to 0. Now we know that we need to restrict that to at most -4. Now that's for this question. Okay, so you really need to see the domain and range at the same time. It's quite difficult analysis, huh? I don't think I will ask this question at your level though. No, don't worry about this. Don't worry about this type in which you need to look at the domain and range at the same time. Okay, but with you, you will need to look at the domain or the range. Okay, like in this case, they give you the restriction on the domain. There will be restriction on the range later on. Okay, now the one we have earlier here, okay, you don't see the restriction on the domain and the range, but at the end you see, oh, my function is not one-to-one. Then there must be some restriction on that x to make it one-to-one. But if I need to know what's the restriction on x here, then I need to know what's the restriction on y here. Then you look back, see what is the y, what are the possible outcomes for the y. Then you trace it forward again to get the restriction for x. Thomas, you just make it very complicated, huh? No, it's not. It is complicated to start with. The problems you were dealing with are the easy ones, such that you don't need to look for so much details. Now, if you are not a detail-oriented person, of course, that's another story, right? You just hate details. Why don't you just give us the conclusion, Thomas? Well, then don't take pre-calculus, take social science. Okay, social science tend to be on the conclusion. Social science people, they use the conclusion they get from STEM people and then apply that to the social science. So they use the conclusion to create policies. Okay, so I'm not saying that they are wrong or they are in any way inferior. No. What they do is different from people who actually in analysis like us. Okay, now let's go to 4.2. I have only 10 minutes, so I guess only part of this point 4.2 can be done. Exponential function. Basic exponential functions have fx equals to a to the x, where the a is greater than 0, not even 0, greater than 0, and the a cannot be 1. The base has to be positive, but even if it is positive, it cannot be 1. Now, if we look at the number line for the base a has to be greater than 0 and cannot be 1. Okay, now suppose the base is greater than 1. If the base is greater than 1, then that exponential function must be an increasing function. It must be increasing. And because it is increasing, it's 1-to-1. Okay. Important coordinates are 0, 1, 1, comma a. You just plug it in. When x equals to 1, the y will be a. Okay. And -1, comma 1 over a. Where the domain is all real numbers. You can plug any x you like. The range is not all real numbers. The range is not even including 0. The range is a positive number from 0 to infinity. not including 0. The y-intercept is 0, 1. No x-intercept. And we have horizontal asymptote on the left-hand side here, y equals to 0. Now, from here, you see that the function is increasing. Therefore, it is 1 to 1. The function is increasing. Now, if the base is between 0 to 1, if the base is between 0 to 1, then the function will be decreasing, yet still positive. Okay, the y-intercept is still 0, 1. This is 1, a, and negative 1, 1 over a. The domain's the same with the other case when the base is greater than 1 is all real numbers. The range also the same from 0 to infinity. The y-intercept also the same. That's 0, 1. X-intercept, both of them don't have x-intercept. Horizontal asymptote also the same, that's y equals to 0, but this time the horizontal asymptote actually on the right hand side. Okay, the further you go to the right, the smaller the value of your y. Now the difference between when the base is greater than 1 and less than 1 is that the function is decreasing. But because it is monotonic, it is still 1 to 1. Okay, so these functions, exponential functions, either the base greater than 1 or between 0 to 1, it will be increasing or decreasing. Therefore, it is monotonic. Therefore, it is 1 to 1. In both cases. Now, that 1 to 1-ness will be used when we solve exponential equation, which I'm about to do right now. On Tuesday, when we come back, we will focus on the graphing. Okay, we will focus on the graphing. So on Tuesday, when we come back, we will do 4.2, 4.3, and 4.4 on Tuesday when we come back. Okay, maybe with 4.5 maybe. Okay, but for now, we say that exponential functions is 1 to 1. Okay, some little detail. So maybe I do that first. Okay, so why that? So what if they are 1 to 1? Means the following. If I have a to the x equals to a to the y, then x equals to y. As long as they have the same base and both of them positive, not 1, then the exponent must be the same. Okay. For example, number 3. How do we use this? 3 to the power of 2x plus 3 equals to 3 to the power of x squared. How do we solve this? Well, by 1 to 1-ness. Blah to the 3 to the blah equals to 3 to the blah implies blah equals to blah. Then you solve it. So either x equals to 3 or x equals to -1. Okay. Now notice that if the function is not 1 to 1, you cannot do that business. Okay, if the function is not one-to-one, you cannot do that business. Let's do it again. Okay, if I have 2 to the x equals to 2 to the 4, then it is guaranteed that x equals to 4. Okay, however, x squared equals to 4 squared does not imply x equals to 4 because square function is not one-to-one. Okay, x squared equals to 4 squared. Does it mean x equals to 4? No. The answer is that x equals to 4 or x equals to -4. You see, that's the power of one-to-oneness. Okay, one-to-oneness, if you see they have the same shoes, then it must be the same shirt. Okay, let me illustrate this one-to-oneness in a very, I know this is strange, but when my colleague actually shared that with me, I say, well, that's the power of one-to-oneness. And then he looked at me and he was, this is what happened. This is what happened. I closed today's lesson with a story on one-to-oneness. Okay, one instructor at SMC, okay, someone pretty close to me, not Mr. Chang, not Mr. Chang. So he's a Mr., it's a he. Okay, now he gave a test, let's say Mr. P then, Mr. Precalculus, okay, gave a test. We were still on campus at that time. Okay, and the time's up. Time's up, and he say, oh, you need to collect that already. Okay, now, but people, not everybody collecting, and he was a bit pissed off. I said, hey, if you don't collect that now, I give you 10 seconds. If you don't give it to me now, then I leave you. I don't take your submission anymore. Okay, that's because he really need to go to restroom. That's the reason. Okay, so after 10 seconds, there were still some people don't turn it in. So he just ran to restroom. He went to restroom. Okay, now if you know a male's restroom, okay, the thing is you can see his shoes underneath. So these students who didn't turn in the test when the time's up actually slide the test under the door of his stall in the restroom. And he was so scared. How do you know it's me? So, Mr. Precalculus, I turned my test to you here. So that student just slid it under his stall. Actually, two or three students. And he was like, how do you know it's me? Oh, from your shoes. It's like, how do you know that it's me from my shoes? Nobody answered that question until he shared that with me. I said, that's the power of one-to-oneness. I don't need to see your whole body to say it's you. All I need to know is, like, I associate your shoes with you. If I see that shoes, then it must be you. Okay, that's the power of one-to-oneness. Okay, I don't need to see the whole picture. As long as you are the only person wear that shoes at Santa Monica, then it must be you when I see that shoes. Okay, but again, if I were him, I was so scared also. How do you know it's me? Imagine if those students actually associate me with my car, right? That's why faculty parking should be different place from student parking, because we don't want you to scratch our car. Even though I don't mind. I mean, if you can find my car and you hate me so much, you want to do that, go ahead. Okay, that's why I don't change my car. Just leave it like that. Nobody scratched my car yet, though. Okay, let me do one more problem and then I'll let you go. Number 7 or number 9. Let's say number 9. 4 to the x times 1/2 to the x to the 3 minus 2x equals to 8 times 2 to the x being squared. For our level now, we'll take a look on all the bases and see if we can change them into a common base. In this case, we'll change that to base 2. Now, the reason is, once they are all in base 2, then we may be able to put them together under one base. So 2 to the 2x times 2 to the 2x minus 3 equals to 2 cubed times 2 to the 2x. But on the right-hand side, on the left-hand side here, this is 2 to the 4x minus 3. When you multiply the same base, you add the exponent. Long time no see, huh? Now, once you have 2 to blah equals 2 to blah, then by 1 to oneness, we get 4x minus 3 equals to 2x plus 3. Kada-bam, kada-boom, x equals to 3. Okay. Now, this is where I will stop. Sorry, I take 2 minutes extra. But then on Tuesday, we will continue with sketching the graph of exponential function. 4.3 is just a slight continuation from 4.2. 4.3 is exponential function with base natural number e. Now, then 4.4 is logarithmic function. Okay, 4.5, we have formulas there. Okay, this is where I'm going to stop. See you then on Tuesday.